Hello everyone, welcome back to another Solid Mechanics review session. In this review session we're going to be covering the 2014 final, so I'll highlight it right here. And basically we are going to go through a solved final, and I'm just going to show you the process I used to solve each question, as well as any tips or tricks I noticed along the way. It might take a while. Of course, this is a 50 question final, so sit back, relax, get comfy, and let's begin. So question number 1 says, consider the matrix M, which is a 3x3 matrix. The matrix M has the following components in the traditional orthonormal basis set. It says, if another orthonormal basis set B' is used, then the components of M' in the representation of M in the basis set B' are given by. So basically, when you have one matrix, and the question's asking you to find the components of that matrix in another basis set or coordinate system, this is the formula you're going to want to use. M', which is the components in the new basis set, is given by Q times M times Q transpose. And if we look here, we're already given what M is. That was right from the question. The only thing that we don't know is Q, and that is actually our coordinate transformation matrix. Now we can actually find Q by using this formula right here. This is the most general formula for the components of Q, where Qij is equal to Ei prime dotted with Ej. So the first thing to note is that is going to be the actual dot product. And if we do that, we get the Q that we have below. Now it's kind of hard to figure out how to actually use this formula. So what we are going to do is we're just going to look at this one component right here, this -1, which is Q32. Now if we were to do this and follow this formula, we know from the formula it's E'3 dotted with E2. So what I would do is I'd look at the question and say, okay, well, in our normal basis set, that E2 is actually just E2. And if we look at the basis set B', that E3 is actually negative E2. So what I would do is I would take the basis vector negative E2, dot it with E2, and then you end up with -1. That's how we got -1 here. But as you can see, there's kind of a little trick to this question, because if we were to look at the rows of Q, we can see that this one is E1, this one is E3, and this one is E2, or negative E2. Let's throw that negative in there really quick. Negative E2. And if we look at this and compare it to actually what we had above, so I'm just going to highlight it over here, it's actually the same. So if you want to find Q really quickly, that is the way. But I always want to show the actual calculations because it serves as kind of a safety net in case, you know what, Clayton, I forgot the trick. Well, you can actually find it using normal calculations, which is my goal. A lot of the times the tricks are hard to remember, of course. Would an exam be an exam if the tricks were easy? Well, probably not. So it's always good to know how to calculate it, which is why I showed it to you. Once we have Q and we substitute it in, we get the following matrix, which corresponds to answer A. So hopefully that helps with question 1. Question 2 says, consider the orthonormal basis set B and let x equal E1 plus E2, while y is equal to E3. It says Z is the orthogonal projection of x onto y. Then, and basically we're trying to solve for what Z is. So the nice thing is right from the question, we're given what Z is. It's the projection of x onto y. And we know that the projection formula that you're given right in your notes looks as follows, where we have x dot y, which will end up being a scalar because it's dot product, divided by the norm of y squared, which will also be a scalar because we're taking the norm of a vector, multiplied by vector y. Now, if we were to actually go through this, we already know that x is equal to 1, 1, 0, that's E1 plus E2, and we know that y is equal to 0, 0, 1. Therefore, we can actually start solving for the components. The first component I solved for was that numerator term where we have x dot y. And if you take x dot y, you'll find that it's equal to 0. So basically at that top term here, we have 0 divided by something times a vector. Well, we know that that in the end is going to be equal to 0 because we have 0 in the numerator. So the answer for this one would actually be D. It's one of those ones where it looks like a complicated question, but basically all we have to do is use the mathematical formula, which you guys know. Well, chances are you guys don't really know it, but you can look it up pretty easily in the lecture notes. So hopefully this wouldn't be too bad of a question. The key thing is knowing that x is 1, 1, 0 and y is 0, 0, 1 because it's a function of the basis vectors. Moving on to question 3, it's a little bit longer, and this one is this is probably one of the trickier questions. If you can memorize one question, it'd probably be question 3. It says the state of stress in a linear elastic orthotropic material, so that's actually going to be the key here. This is an orthotropic material, is described by the Cauchy stress matrix, which is basically a diagonal matrix. And it says if the Young's moduli are E11, which is 200 MPa, E22, which is 1000 MPa, and E33, which is 200 MPa, while the value of Poisson's ratios are V12 is 0, nu13 is 0.2, and nu23 is 0.4, then the strain component E22 is equal to, so basically all we're doing is solving for that strain component. Now, if you go to the lecture notes for orthotropic materials, you can find that this right here is, by definition, the formula of epsilon 22 for an orthotropic material. So all we have to do is find each one of the components. If we look at the first component here, it has that nu12. And if we look at the question, well, we see that nu12 is 0, which is why I was able to cancel it out really quick. So then it just leaves kind of that second third, which is sigma 22 over E22 minus V32 over E33 times sigma 33. Now if we look here, E22 we're given, sigma 22 we're given, sigma 33 we're given, and E33 we are given. So the only thing that we actually don't know is nu32. Now the most common mistake I will see students use is they will pick nu23. But remember, for an orthotropic material, nu23 and nu32, they are actually different. However, since the matrix must be symmetric, we have this formula right here, where nu23 over E22 is equal to nu32 over E33. And if we look here, we know what 23 is, we know the two e's, so we can actually solve for nu32 as simply nu23, where we take E33 and then divide it by E22, and you get that this is going to be equal to 0.08. Once we know that it's 0.08, we can substitute it up into the formula above, and basically when you do all your calculations in your calculator, you get that this is equal to 0.032. So again, this could be one of the trickier questions because you have to remember that for Poisson's ratios of orthotropic materials, they are not necessarily equal to each other. You actually have to calculate them. So that's the trick to question number 3. If we move on to question number 4, it says that the shown axially loaded beam is made of a linear elastic material with varying E, such that E is equal to 200 minus 20x1. If the distributed load is equal to 0 and the beam is subjected to an axial load of value P, then the differential equation in terms of the horizontal displacement is given by, so basically it just wants the differential equation for this beam. Now if you look at the notes, the differential equation of a beam under axial load is as follows, where we have the derivative of EA multiplied by the derivative of our deflection function, plus P, where this smaller p is actually equal to our distributed load, is equal to 0. So the first thing that I did really quick was I said that P term to 0, and that's because the question says that the distributed load is equal to 0. So then we are left with basically just that left-hand side. Now if we look here, we actually have to use a product rule to figure out this differential, because if we look at the terms that we're differentiating inside, which are these terms right here, two of those terms are a function of x1, namely E, as well as the derivative of our deflection function. So what I did is I took product rule to obtain the following expression down here, where we have A times the differential of E multiplied by the differential of deflection, plus EA multiplied by the second differential of deflection, and we know it's going to be equal to 0. Now if we actually look closer, both of these terms have an A. So what I did was I factored out the A over here, and since this is equal to 0 on the other side, I just divided both sides by A, so I kind of canceled the A, if you will. From there, I was able to simplify this even better, I guess, because we know that since E is equal to 200 minus 20x1, well then the differential of E is simply going to be negative 20, and I substitute them into my 2e terms to get the following expression, which I will highlight in pink right down the center here. And as we can see, this corresponds to answer number E. So it's a very nice question. All it takes is a little bit of simplification of the differential equation, which you are all experts at. So I believe that you can do it. Question 5 is a bit of an easier question. It says that the limits of Poisson's ratio in a linear elastic isotropic material are given by the idea that Poisson's ratio has to be greater than -1, but less than 0.5. If a material does not abide by these limits and has a Poisson's ratio less than -1, then the following unstable behavior will be observed. So answer A, which I already marked off as incorrect, says that the positive hydrostatic stress will be accompanied by a negative volumetric strain. The key here is that whenever you see this volumetric strain, oops, I forgot to switch back to yellow. Give me 2 seconds. Volumetric strain. Basically, this is related to having a Poisson's ratio greater than 0.5. If we look at the question, we are investigating the case where it's less than -1. So although answer A is true for a Poisson's ratio greater than 0.5, it's not true for less than -1. What is true for less than -1 is that a positive shear stress will be accompanied by a negative shear strain. So we know that the answer in this case is going to be B. So again, it's one of those little tricky questions. Both of these behaviors are expected, but they occur at the different bounds of Poisson's ratio. This question is a really good question, question number 6. It contains one trick that I think would get a lot of students, so we're going to go over that specific trick. It says that the potential energy of a mechanical system is given by the equation 20 theta cubed minus 60 theta, where theta is the angle of rotation of the system. Then the following is true regarding the position of a stable equilibrium. So the key here for stable equilibrium is the idea that the potential energy of the system must be minimum. Okay, there's the key. It must be minimum. So for a stable system, we know, oops, that's the eraser. Don't want to do that. For a stable equilibrium, the derivative of the potential energy must be equal to 0. Again, this has to do with the mathematical concepts of maximums and minimums. So if you were to take the derivative and set it equal to 0, you get the following equation where theta squared is equal to 1. So we know that theta can be either plus or minus 1, so most students would pick answer C. But remember, one of the things that we don't really talk about in class a lot, because this is always the case for us, but if we were to go to a general system, is that this potential energy must be a minimum, right? It must be a minimum. If we look here, we have 2 different options of theta, but as we see, if we were to look at theta is equal to -1, this is actually a maximum. So this would actually be a very unstable system. And how do we check that? Well, what we do is we take the second derivative, which I did over here, which we found as 120 multiplied by theta. Now, for this to be minimum, this term has to be greater than 0. So the only way to have 120 times theta greater than 0 is if theta itself is positive. So that's why I have down here that theta 1 is minimum when it's equal to 1, and it's going to be maximum when theta is actually equal to -1, because we have a negative second differential term. So for this question, the answer would be A, where it's only in stable equilibrium if theta is equal to 1 radian. Again, we don't really look at the maximum and minimum case, because we said for our systems, if we have a positive, basically if we have elastic moduli that follow the energy restrictions we talked about, it will always be a minimum. But for these general mechanical systems, you actually have to go and check whether it is a maximum or minimum, and we do that by taking the second derivative of the system. So it's one of those really tricky questions where I guarantee a lot of students would pick C, but it's actually only A because one of them is a maximum rather than a minimum. Moving on to question 7, it says let I be a 3x3 identity matrix and consider the matrix A, which is equal to P, where P is a scalar, times I. Then the following is true except, so basically we have to look at which one is false. So what I do for these type of questions, I find it easier, is I like to just write out what it is. So we know that A is equal to Pi, so we have that nice matrix of basically poo. And the reason why I say that is because that's all I see now is just poo. Now, if we look at this matrix, we actually have two very beautiful things. The first one is that this is a symmetric matrix, and the second one is this is a diagonal matrix. Now, for a symmetric matrix, we already know that by definition, A has to be equal to A transpose. So if we look at option B, we know that that is actually correct. For the diagonal matrix, we know that the third invariant, which is equal to the determinant of A, is simply going to be the three eigenvalues multiplied by each other. Now, for a diagonal matrix, the diagonal values are actually the eigenvalues. So we know in this case, all of the eigenvalues are just going to be equal to P. So if we go P times P times P, we get P cubed, and therefore we know that option D is actually also correct. The last thing we know is that the the trace, which is the first invariant of A, and that's equal to the trace of A, is going to be the sum of that diagonal components. So if we look here, we have P plus P plus P, which gives us 3P, and if we look at option A, we actually see that that is incorrect. So we know that option A is actually going to be incorrect, so therefore it has to be option A. For option C, which is the inverse, it's one of those things that if you want to, you can prove it or calculate it, but I usually try and save inverse ones for last, because they usually take the longest to do. So if you can prove a couple of them and then eliminate one, chances are you're good to go, so you'll be just fine. All right, question 8. It says, let I be the 3x3 identity matrix, and consider the matrix A, which is Pi, so it's the same as before, and it says then the matrix A squared, which is A times A, is given by. So for this one, it's kind of just a little bit of a proof where we know that A squared is A times A, so I can rewrite it as Pi times Pi, which will give me the following form. Now notice that I have I times Pi. Well, we know that Pi at the end there is actually equal to A. And if we were to take the identity matrix A and then multiply it in, well, we know that this term IA is simply just going to be A. Because if I multiply something by the identity matrix, well, it just turns into itself. So we can actually do a nice little proof to simplify this. But it's one of those nice things that if you're given access to Mathematica, if your professor is extremely generous, you can just type this in and actually solve it really quickly to kind of verify it. You don't actually have to go through the actual proof, which is nice. Question 9 is again that 3x3 identity matrix where A is equal to Pi. And it says then the following is an eigenvector of A. Well, this is actually nice because if we look here all the way back up, we know that A is already a diagonal matrix. So the only way that we can transform this and still get a diagonal matrix is if our Q matrix, our transformation matrix, which I'll put in purple, I guess purple will be my pen, if this is equal to the identity matrix itself. Actually, I won't write it out, I'll just put I. This is the only way. Now keep in mind that things can be scaled differently, so I can have, let's say, instead of 1, 0, 0, I can have 5, 0, 0. But if we were to look at the three options here, X, that's the first row of I, Y, that's the second row of I, and Z, that's the third row of I. So actually these would all be correct. So this is actually one of those little trick questions. It's not too bad. I think most of you will get it. Now, as you're going to see, Dr. Sammer, who taught this course before me, loves these types of questions. You're going to get so sick of this cube by the end of this review session. It says, the shown unit length cube is in a state of stress represented by the stress matrix, sigma, which we are given. It says with the following components. It says then the normal stress on plane BCGO is equal to, and for these types of questions, the best thing that you can do to start off is highlight which plane they are talking about. So that's why in red here I circled which plane. I want to know which plane I'm actually concerned about. Now, whenever you're dealing with these stress types of questions and you're given a stress tensor, the first thing that you're always going to need when solving for them is the normal vector describing this plane. So we know that the normal vector is actually going to be perpendicular to this plane. So we know that this, for this specific case, since it's going along the negative E1 axis, is going to be negative 1, 0, and 0. Once you have that normal vector, the rest is actually a piece of cake. Because if you look at the notes, we basically can solve for three things. The traction vector, the normal stress, and then the shear stress. For this question, it just wants the normal stress. So Tn, our traction vector, is going to be transpose of sigma multiplied by n, Well, we know what n is, we know what sigma is, so we can calculate it as -1, -4, -5. And then the normal stress is going to be our traction vector dotted with that n vector. So we're going to have -1 multiplied by -1, which gives us 1. We're going to have -4 multiplied by 0, gives us 0. And we're going to have -5 multiplied by 0, which gives us 0. So we know that the normal stress is actually just going to be equal to 1. Now, it's one of those nice things that you don't actually need to do these calculations for this specific case, because we know that this vector itself, the normal stress of this plane is aligned with the E1 axis. So if we ever have something aligned with an axis, in this case we have the E1 axis, as we can see n is parallel with it, we know that this is actually just going to be the stress component sigma 1, and as we can see from our tensor, it's actually just equal to 1. So again, it's one of those things, if you know the tricks, it'll help you kind of save time, but if you don't, that's okay, because we know all the calculations to verify everything. So even though there are a lot of tricks to these questions, I still like to show you the calculations just to make sure that you're all comfortable with everything. Question 11 is kind of the same thing, but now it wants the shear stress on that face. What's nice for us is, since this is identical to the question above, the plane is identical, we already know that n is going to be -1, 0, 0. But notice that the stress tensor is actually different. So when we find our traction vector in this case using the same formula, it's going to have slightly different components. And we can find our normal stress by taking this traction vector and dotting it with n to get 1. From there, we can actually take it a step further by solving for the shear stress with the following formula, where it's going to be Tn minus sigma n times n, and this right here is going to give us a vector. From there, what we do is we actually take the norm of that vector. So what I like to do to start off is I like to find out just what this vector is equal to. So all I did was I took our traction vector right here, I subtracted it from our normal stress multiplied by n, and then I ended up with the vector 0, -3, -4, and then I just found the norm of that vector right here, which gave me 5 in the end. So from there we were able to find things pretty easily. Now, the one thing to kind of note about this is notice that that 5 component wasn't given as any of the shear stresses. In the last example, we said if we're dealing with normal stresses along an axis, it's pretty easy because we can just find it from the tensor itself. But for this particular case, we actually had to do some calculations. We found that it was equal to 5. We're good to go. As you can see, the calculations are pretty simple. It's nothing too crazy. Now, this question is great because it's very similar to the one before, but it has a trick to it, and that is this. It gives us our cube that we are so used to now, and it wants the normal stress on the interior plane ADGO. So again, the first thing I do is I highlight that plane because I want this normal vector n. Now, if we were to look at this plane, we can see that the normal vector n could be expressed as -1, 1, and 0. And I guarantee a lot of students will put it as such. The thing that you have to remember for this vector, which I'll put in purple, is this must always be normalized. Alright, it must always be normalized. That's why I have it as -1 over root 2, 1 over root 2, and 0, rather than -1, 1, and 0. If you don't normalize it, all your calculations are going to start getting a little bit mixed up. Now, once you have n, you can find the traction vector. Again, same process as before, and then you can find the normal stress by taking that traction vector and dotting it with n. So you get -2.5 MPa. Again, the whole trick to this question was ensuring that your normal vector n, making sure that that bad boy was normalized. If it's not normalized, well, you're going to get a different answer. And I guarantee, even though I didn't create this exam, I guarantee that would be those two answers right there if you don't normalize it. So make sure that you actually normalize it. Question 13 says the stress matrix is always symmetric because of, well, before we even look at the answers, we know it is symmetric because of the balance of angular momentum. And this is basically taking a differential slice and taking moments. So that's going to be the key here. So option A is, I'll just go back to purple, the symmetry of the strain matrix. That's untrue. Option B, the material is linear elastic. That's untrue. And C, the sum of the internal moments is equal to 0. That's another way of saying the balance of angular momentum. So we know that it will actually be option C. Okay, so it's one of those ones that hopefully you don't get tricked up. Another key to question 13 is that it says that the stress matrix. Typically when you see this question, it's always having to do with the constitutive law matrix. And in that case, that's because of energy preservation, which is linear elastic materials. So if that was the case, it would be option B. But the thing to remember is that if we look at this question, it doesn't care about the constitutive laws. Its only concern is the stress matrix. So that will be that one. All right, question 14. It says that the position function of a deformed continuum has the following relationship, where beta is a positive real value. Then the small strain tensor is given by, and this is one of those ones where you can look at it and kind of figure it out because it's in a state of pure shear. But if you forget about pure shear, you can look at this and say, okay, I actually know the process of finding strain from our displacement functions. The first thing to do is to find the from position functions. The first thing to do is find the displacement function u, which again is just going to be small x minus big X. So for example, if I were to look at this first row here, where we have x1 plus beta times x2, and I subtract x1, well then all I'm left with is beta times x2. For the second row, I subtract x2, and for the third row, I subtract x3. Once I have my displacement function, I can find the displacement gradient by simply taking the partial derivatives of each of those displacement terms. So if we look right here, what I did here was I took the first row, which is beta x2, and I took the derivative with respect to x2 while I'm left with just beta. And once we have this displacement gradient, we can actually solve for our strain tensor, or more specifically our small strain tensor, using the following formula, and you'll end up with 0, beta 0, beta 0, 0, and 0, 0, 0, which is option B. So again, if you don't know the tricks, it's very simple to calculate. As you can see, it only took a couple of lines. You will be good to go. Now, question 15 says that the position function of the shown unit length cube after deformation follows the following relationship. It says, using the small strain matrix, the strain along vector OE after deformation is given by, and it has a bunch of different options. Now this is kind of related to that previous question where we talked about stress, where it's very important to know which direction it wants. In this case, it wants vector OE. So if I were to highlight OE and I were to show it on our cube, we know that this is the strain in basically the E1 direction. Now we know that the strain in the E1 direction is epsilon 1,1. So if we can figure out what epsilon 1,1 is, we actually know what the question is. To do this, we use the same process as before. From our position functions, I find our displacement functions. Again, simply just subtracting big X. From there, I was able to find the displacement gradient by taking all those differentials. And then I was able to find the strain tensor using our strain formula. After that, once you have the strain tensor, you just need the component you're looking for. In this case, we were looking for E11 right here, which we see that it's actually equal to 0. It's a lot of work for it to end up being equal to 0, but it is what it is. So we know that in this case, it's going to be option A. So hopefully that wasn't too bad. Again, the key here is knowing the direction of the vector that they want the strain along. If they wanted it on a diagonal direction, well, we'd actually have to take a couple more steps, but luckily for us, it was along one of the basis vectors, made our lives a lot easier. Question 16 says that the deformation of the shown unit length cube is described by the following small strain matrix. And then it says, then the small strain along the direction OD is given by, and this is related to what I was just saying, where if it was the strain in a diagonal direction, we actually have to do a little bit of extra steps. The first step is you always have to define the direction. So we're talking about OD, so we want a vector that goes from O to D. Well, we know that that vector is simply going to be 1, 1, 1, because it's a unit length cubed. All right, cube, not cubed. Once we know the direction, we can actually find the strain in that direction using the following formula, where we have that vector dotted with the strain tensor multiplied by that vector, and then divided by the magnitude of that vector squared. So once we know the vector and once we know the strain, which we do, we can simply solve for everything. The first one is if I were to take the norm of that vector squared, I get 3. All right, not too bad. And then if I were to take that vector and dot it with our strain vector times the direction of the vector, I get 0.15. From there, I just take that 0.15 divided by 3, I get 0.05. So therefore, we know the answer is actually going to be equal to D. If you ever are asked for the strain in this arbitrary direction, you always want to use that formula. All right, that formula always works. Even if you were to forget up here that the strain would be equal to epsilon 1, 1, you know that your vector in this case would have been just E1, which is equal to 1, 0, 0. And if you were to plug this into this formula down here to solve for it, you would have found 0. So it's one of those things that you can forget the tricks and completely rely on the math, which is always nice to do in case you're ever stuck in a tough spot. Question 17 says the deformation of the shown unit length cube is described by the following small strain matrix. It says, then, using the small strain matrix, the angle between OB and OG after deformation is, and if you ever have one of these angle cases, it's a little bit tricky because the formula can get pretty long. Basically, there's two steps involved. The first one, like before, when we were dealing with the strain in a direction, is you need to have vectors defining the two vectors that you want the angle between. So the first one is OG, which we know is simply just the vector E3. And then the second one is OB, which is simply just the vector E2. Once you know the two vectors, you want to come to this formula here. This formula is given right in the notes, so you can just substitute everything in. If we look on the right-hand side first, we are going to have E2 dotted with the strain times E3 divided by the norms of both of these, which we know is going to be equal to 1. And we get that this is equal to 0.04. Not too bad. If we look on the right side, we actually have a bit of a problem because we have theta, which we're trying to solve for, but then we have another cosine theta. Now this theta I is the initial angle between these two vectors. If we were to look at this cube right now, we know that the vectors start off perpendicular or 90 degrees from each other. So once we substitute 90 degrees in, we see that this second cosine theta I term, it goes away. So we're left with cosine theta over 2 is equal to 0.04. We can rearrange it to the formula above, and we can find that theta is equal to the inverse cosine of 0.08, which corresponds to answer number D. One of the trickier questions for sure because it has to do with angles, and the angle formula is pretty gross if we're being honest with each other. But if you know all the steps, it's pretty simple because all the vectors are basis vectors, which simplify quite nicely. If we look at question 18, it says the longitudinal green strain along a specific direction is given by 0.105. If the vector has an original unit length along this direction, then its length after deformation is equal to, well, this is pretty simple because if we know this green strain, we have the following formula, where it's 1/2 of lambda squared minus 1, where lambda is our stretch ratio. If we look at this, our only unknown is lambda. So what I'm going to do is I'm going to solve for lambda, and I find that lambda is equal to the square root of 1.21, which is equal to 1.1. And we know that this lambda, which is equal to our stretch ratio, which is L divided by L naught, and L naught is equal to 1. Well, therefore, L must be equal to 1.1, which is option number B. In these uniaxial strain cases, the questions are actually pretty simple. All you really need to do is solve for the stretch ratio, and then from there you can do whatever you want. Once I know lambda, I can also figure out things like the engineering strain, the true strain, all that fun stuff. But this question just wanted the deformed length, which wasn't too bad at all. Question 19 says the state of deformation inside a linear elastic isotropic material is described by the following small strain matrix. If the Young's modulus is 200,000 MPa and the Poisson's ratio is 0, then the hydrostatic stress describing the state of deformation is given by. Now, the key thing for hydrostatic stress is that all we need to do is take our three stress components in the basis directions, E1, E2, E3, and then divide it by 3. So all I actually really need for this question is sigma 1, 1, sigma 2, 2, sigma 3, 3. Now what's nice for us is since the Poisson's ratio is 0, we can actually use the following stress-strain relationship, where sigma is equal to E times epsilon. Now if we look here, our epsilon 1, 1, 2, 2, and 3, 3 are all the same. And if that's the case and we have this linear relationship, well, we know that sigma 1, 1, 2, 2, and 3, 3, they must all be the exact same. Now if we solve for them, we find that it's equal to 1,000. So all I need to do there is take 1,000 plus 1,000 plus 1,000, so sigma 1, 1 plus 2, 2 plus 3, 3, divided by 3, while I'm left with 1,000, which is option number C. So not too tricky of a question. The key thing that I think most students would mess up on is they like to forget to divide by 3. So this is why they have option D, which is 3,000, and I guarantee a lot of the students would be picking that one. So keep in mind for hydrostatic stress, we always divide by 3 at the end. Coming up to question 20, it says that the state of deformation inside a linear elastic isotropic material is described by the following small strain matrix. And if we look at this small strain matrix, it is the exact same as before. And it says if the Young's modulus E is 200,000 and Poisson's ratio is 0, then the maximum shear stress describing the state of deformation is given by, and this is actually kind of a trick question, because again, if we look here, we can see that this small strain tensor is the same as before. The material properties are the exact same as before, and we said that in this case, it's actually hydrostatic. Now, we know for a hydrostatic stress state, there cannot be any shear. That's the trick here. We know that since this is hydrostatic, there cannot be any shear, therefore our shear is actually equal to 0. Now, if you want to forget about all that and do the math to prove it, you definitely can, but you're still going to find out that there is going to be no shear in our system because it is hydrostatic. So again, a little bit of a tricky question. Question number 21 says the shown figure represents a specimen under confined compression test. The vertical stress is negative P, where P is a positive scalar value, while the confining stress is applied to ensure that the specimen does not expand or contract laterally. The specimen is isotropic linear elastic with the Young's modulus E and Poisson's ratio nu. It says basically the confining pressure is equal to, so all we need to do is find that. The key to this question is if we know that our specimen does not expand or contract laterally, well then there has to be no strain in the E11 or E33 direction. We also know that in the 1,1 and 3,3 direction, there is a stress used to confine it, which I'm going to call C. And in the 2,2 direction, we are applying a stress of negative P. Once you have these variables, all you need to do is find an equation for either epsilon 1,1 or 3,3 because we know it's equal to 0. So what I did is I took my equation for a linear elastic isotropic material. We know it's equal to 0, which I have kind of a little bit later on. And all I did was substitute all the parameters. Sigma 1, 1, 2, 2, 3, 3, we know what those are. And nu and E, those are going to be the same. So once you simplify it, you get the following relationship where negative nu times P is equal to C multiplied by 1 minus nu. You can solve for C as negative nu P divided by 1 minus V, which corresponds to answer number A. So the trick here that you need to know is that if something is not expanding, the strain has to be equal to 0. If we didn't know the strain, we actually couldn't solve for this question. The only way that we were able to solve for it is we knew that epsilon 1, 1, which we expanded out, we knew that that was equal to 0 because it does not expand nor contract. There's the trick there. Question number 22 says that the shown elastic cylinder is subjected to a stress as depicted in the figure. The original diameter of the cylinder is equal to 15 millimeters. If E is 20 GPa and the Poisson's ratio nu of 0.4, then the diameter of the cylinder after applying the pressure is equal to. So basically what we want is we want to find the strain. It's kind of just like before actually, where we want to find the strain in the E1 or E3 direction. Because once we know the strain in that direction, we can actually find the change in the diameter's length. Just like before, we can use the same formula that we had above, and we actually know all of the components. We know what E and nu are, and we know what sigma 1, 1, 2, 2, and 3, 3 are. Sigma 1, 1, and 3, 3 are negative 400 MPa, and sigma 2, 2 is negative 600 MPa. Now, once you do all the calculations, you will find that epsilon 1, 1 is equal to 0, which means that it is not expanding nor contracting. So we know that the diameter after the pressure is applied is going to be the exact same, which is 500 millimeters. It actually satisfies the case that we had just above here, where we have that confining pressure. Pretty fun. I don't recommend trying to see if it is the confining pressure right off the bat, because that's a lot of work that might be incorrect. All right, so 23, it says a viscoelastic material is a material that exhibits the following. Now, the key thing for viscoelastic is that it is time dependent. That's the whole definition of viscoelastic. So it says A, the material exhibits creep. Well, creep is time dependent, so that's true. The material exhibits stress relaxation. Well, that's also time dependent, therefore that's true. The stress strain curve of the material is dependent on how fast the load is applied. Again, time dependent, so that's true. So the answer would actually be D, all of the above. Because again, all of those things that they listed were all time dependent phenomena. So not too bad. It says an elastic material that exhibits the following. An elastic material is a material that exhibits the following. A, the material exhibits creep. Well, that's viscoelastic. A material exhibits stress relaxation, also visco. And the stress strain curve of the material is dependent on how fast. Again, that is visco. But option D here, the stress strain curve of the material is independent of how fast the load is applied. That is a true elastic material, so the answer is going to be D. One of those kind of fun ones. All right, next question. It says that the position function of an object after deformation is described by, and this is one of the harder type questions. It says, which is the following true regarding x? It's basically asking what kind of motion is going to happen. Now, the best thing I can do or recommend for this type of question is try to get it into the form where we have a matrix multiplied by basically our big X vector. Now, if we were to do that, we would get the following matrix times big X, but in order to make it truly this form, we would have to add a constant matrix right here. Now, if we were to look here, we can actually see that that first matrix, the one with the 1, 0, 0, 0, 1 over square root 2, that's actually a rotation matrix. And if we were to look at the constant matrix at the end, well, we know that that is a constant matrix describing rigid body displacement. And for rotation, we know that that is going to be rigid body rotation. So for this particular case, since we have Q and C, we know it's actually going to be option C, which is X describes rigid body motion, which is a combination of rigid body displacement and rigid body rotation. So it's one of those little fun questions. Question number 26 is the same thing, where it says, what is this describing? And if we were to simplify it into this form, we are going to have a matrix times big X. And then in order to do this for this particular matrix, we have to have that constant vector. As we said before, that constant vector is rigid body displacement. So we would need that in our answer. And then if we were to look at that matrix before the big X vector, we can see that that is not a rotation matrix, but rather a simple shear matrix. And the reason why is because all the diagonal components are 1, but we have this one term here. We know that if we only have one term, it is simple shear. If this term right here was also 0.01, that would actually be pure shear, which I believe we talk about a little bit later. So we know that this is going to be rigid body displacement, again, because we have that constant C vector and some shear deformation, more specifically simple shear deformation. So hopefully that wasn't too bad. Moving on to the next one, it says the position function of an object after deformation is given by, and it says if the material is linear elastic isotropic with the Young's modulus and Poisson's ratio of E and nu, then the strain energy per unit volume is given by. Now the thing to keep in mind is that for strain energy, this is going to be the formula for your strain energy density. It's going to be 1/2 multiplied by the summation of sigma ij times epsilon ij. Now it looks like it's going to be really gross, but if we were to look here, what we can do with our position function is we can solve for our displacement function, which we can then solve for our displacement gradient, which we can then solve for our strain tensor. Now if we look at our strain tensor, we have 1, 2, 3, 4, 5, 6, 7 components that are actually just going to be 0. So this formula that I said was really gross, well, it actually simplifies into 2 times epsilon 1, 2 times sigma 1, 2, and then divided by 2. So the 2's cancel right off the bat. Now if we were to look at this formula, it's not too bad because we know what epsilon 1, 2 is. The only thing that we actually don't know is actually what sigma 1, 2 is. But we can find that because for a linear elastic isotropic material, we know that epsilon 1, 2 is equal to sigma 1, 2 divided by 2g. We can rearrange this to find sigma 1, 2 as 2g epsilon 1, 2, which we can simplify into E times epsilon 1, 2 divided by 1 plus nu. From there, we can substitute it back as sigma 1, 2 to find our strain energy is equal to E times epsilon 1, 2 squared divided by 1 plus nu. And if I were to substitute everything in, this is actually what I get. I get 2.5 times 10 to the negative 5e divided by 1 plus nu. If we look at our answers here, we actually don't have that particular answer. What's nice for us, though, is we know that 2.5 times 10 to the negative 5, well, that's actually equal to 0.001, and I guess there's a little bit of a typo, divided by 4, 1 plus v. Basically 0.001 divided by 4. I'll correct this little typo in the exam solution above. But that's basically how we find it. Again, all we need to do is find the stress and the strain components. Turned out a lot of them were equal to 0, so we were on easy street for the most part. Moving on, we're question 28. It says the position function of an object after deformation is described by, and it says then the following is true regarding E small and E green. So it's kind of the same what we had before, where if we know the position function, we can find the displacement function. From there, we can find the displacement gradient, and then we can find our strain tensors. So our small strain tensor, which is 1/2 of nablu plus the transpose nablu, which I called E small, well, we'll actually find that that's equal to 0. But if we were to look at the green strain tensor, which is 1/2 of nablu plus nablu transpose plus nablu transpose times nablu, we find that there are some non-zero axial strain components. Remember, the green strain tensor is more accurate because the small strain tensor does assume small deformation. If we look at our answers above, we can see that it's going to be answer B, which is E small predicts 0 strain components throughout, while E green predicts some non-zero axial strain components. Well, that's exactly what we found out. So we know that the answer is going to be equal to B. All you need to do for this question is just solve for our strain matrices, and then by visualization, you can see which one is correct. All right, we're going to move on to question number 29. It says the shown plate has a thickness of 1 unit and is subjected to a constant state of plane stress described by the following matrix. When applying the principle of virtual work to the plate, the plane displacement is considered as u star, which is 0, a times x1, where a is greater than 0. Now the question actually says, then the external virtual work due to the traction vector acting on edge A is given by. So basically we want the external virtual work of the traction vector on surface A. Now this is going to follow a similar procedure to what we did for stresses, where the first thing you want to do in these cases is you need to define what this surface normal vector is. So I usually like to draw the surface, and then we know that the normal vector is going to be perpendicular to it. From here we can see that n is actually equal to -1, 0. From there we can find the traction vector by taking our stress tensor, transposing it, then multiplying it by n to get 2, 2. You're going to need this traction vector because if we look at the definition of external virtual work, we're basically integrating the traction vector dotted with our virtual displacement. If we look here, we can see that this is going to be 2 times 0 plus 2 times ax1, where we know that this is actually just going to result in ax1. So the next thing that we actually need to do is we can substitute it in, where we can find we're having the integral of ax1, and then we have to find the limits. If we actually look at this surface, we know it goes between 0 to basically in the x2 and x3 direction. We know that since x3 is just a thickness of 1 unit, we don't actually have to include it because we would just be multiplying by 1. So all we would do is we'd integrate over x2. So notice in my integral, I'm integrating over x2. But the key here is this. If we integrate over x2, we are actually left with just a times x1. Nothing actually happens. The last thing you have to realize is that this entire surface, and I'm going to erase kind of some of the highlighting here, this entire surface occurs at a location of x1 is equal to 0. So what you actually do is you substitute that value in. Well, then you can see that we're actually integrating 0. So we know that this is going to be equal to 0. These kind of questions, external virtual work, they're never too bad. I think the biggest problem students have is figuring out what to integrate with respect to. Again, if we were to look at this shape over here, we can see that the shape goes in the x2 and x3 directions. Therefore, that's what we would integrate over. That third direction, well, we can actually just substitute a value in because, again, for this particular surface, x1 is always equal to 0. We can change it up a bit. As we can see, this question is the same as before, but now we're looking at surface numbers, or surface C. So again, the first thing I want to do is find that normal vector. Remember, this always has to be normalized. And we can find it as 1 over root 2, comma, 1 over root 2. From there, I'm going to do the exact same procedure where a traction vector is equal to the transpose of sigma times n, which is equal to negative root 2, comma, root 2. And then from there, I can find out what this term is inside of my integral by simply dotting our traction vector with our displacement function, which we were given. So from there, we can find that this function is actually equal to a root 2 times x1. So I'm going to substitute that in as follows right here. And then we have to figure out what we integrate with respect to. Now this one's a little bit tricky because if we look at the surface, it goes in both the x1, x2, and x3 direction. Now this is a bit of a problem because typically what we do is we integrate over the actual surface. And if we look at our figure here, this would be the surface itself, this purple line, which I'm going to call L. So what I did was I put my integration limits as follows. I'm going from 0 to L with respect to L, which is again that purple surface that we defined. What we can actually do is we can actually figure out what this dl term is equal to. Looking kind of close up to the figure, we know that x2 is actually equal to 1 minus x1. That's the equation governing this line. If I were to take the differential, we know that dx2 is actually equal to negative dx1. I don't know why I don't have the negative there. Let me just fix that really quick. Negative dx1, as we're going to see, it doesn't matter. Now, since these two actually create a triangle, and dl is the hypotenuse, we know that dl is simply going to be the square root of dx1 squared plus dx2 squared, which is the same as dx1 squared. So this is actually equal to root 2 times dx1. From there, I can substitute that back into my integral. So I have the same thing as before where I have a root 2 x1, but now I have root 2 times dx1, and we know our integration limits now are over the x-axis, so 0 to 1. I can solve for it as follows, and then I can find that this is actually just going to be equal to a. So it's not too bad at all. We can see that that is going to be option B. This would be one of the trickier questions I would say you would find in the final exam, because this has a bit of tricks when it comes to finding those integration limits. I personally don't like to include these on my final exam. I'm not saying you won't see it. You might see it. I don't want to say that it's not going to be on the final, but it's one of those things that to me this is more of a math proof rather than actual solid mechanics, because you will still know all the solid mechanics formulas. The only thing that students have trouble with is the math, and the math is a little bit separate from the course itself. All right. Question 31 says that the shown cuboid is subjected to a state of stress described by. It says if the virtual displacement field U star is equal to 0, a, x2, and 0, then the external virtual work due to the body forces vector is given by. Well, we know that for external virtual work, for body forces, we actually need that body forces vector, and it's not given to us. But we know that this state of stress actually has to be in equilibrium. So what we can do is we can take our three equilibrium equations to solve for the three components of our body forces vector. Now remember that for these equilibrium equations, all we're doing is taking the derivatives going down each row, and then we're adding that body forces vector. So the derivative of 2x1 with respect to x1, that's going to be 2. The derivative of negative 2x2 minus 2x1 with respect to x2 is negative 2. The derivative of 0 with respect to x3 is 0. And then we have plus rho b1. If we solve here, we can actually find that rho b1 is equal to 0. If we go down the second row and solve for rho b2, we find that rho b2 is equal to 0. And then for the third row, it's all zeros, so we know that row B3 is going to be 0. Therefore, our body forces vector is actually equal to 0. And if we're not applying any forces, well, then we know that there is no work done on the system, so we know that the external virtual work is actually going to be equal to 0, or option D. This question is kind of funny because it looks like a virtual work question, but we actually didn't have to do any virtual work. All we actually needed to do was solve for our body forces vector. So this is more of an equilibrium type question. Now question 32 is just really gross, if I'm being honest. It gives us a cube, it gives us a state of stress, it gives us a virtual displacement function, then it says that the total external virtual work from both traction vectors and body forces is given by, and for this one, you basically just have to go over each one of the surfaces, and it's not too bad because we know the formulas for both. So if you go through them, you will find that we have 0, 4a, 4a, 0, 0, 0, and our body forces vector is negative 4a. So basically at the end here we have 4a plus 4a minus 4a, which gives us a total of 4a, or option B. Again, all you need to do to find these is just use the formulas that we have before. It's really simple to do, it's just long and tedious, which I know students really hate. So chances are you wouldn't see one of these from me. It's just too long for a single multiple choice question. Question 33, this is a good one. It says, consider a metal that follows the Tresca failure criterion, which we know has to do with shear. It says, when the metal was subjected to a uniaxial stress, the material failed when sigma 11 was 300 MPa. The metal was then subjected to a state of stress defined by the following stress matrix. So the first part here is it says that under uniaxial stress, sigma 11, which would be equal to our yield stress, was 300 MPa. This is important because we know that our material will fail at a maximum shear stress of sigma y divided by 2, or 150. So we know that our maximum shear is 150. Now, the maximum shear is what it fails at. It's not what's actually applied. What's applied, which I call tau A, is 1/2 of the maximum between the differences in the principal stress components. So if we look at our matrix here, it's not in principal form. What we would actually have to do is diagonalize the matrix to find its eigenvalues. From that, all you have to do is find the maximum difference between the eigenvalues. You'll see that the eigenvalues are negative p, p, and 0. So the first difference is negative p minus p, the second difference is p minus 0, and then the third difference is negative p minus 0. Well, we know that in option 1 where we have negative p minus p, which is negative 2p, and then take the absolute value of 2p, we know that our applied shear stress is going to be 1/2 of 2p, which is equal to p. And then what we do is we take this applied shear stress, we set it equal to the maximum, and we can see that p is actually equal to 150. So it's one of those ones where it just happens to be 150, but it wouldn't be all the time. So I wouldn't get used to it. You're going to have to do a little bit more than just solving for that maximum shear stress. But as we can see, it's not too bad at all. Question 34 is kind of a similar question, but instead of Tresca, it wants von Mises. Now, von Mises is, in my opinion, easier for students because all you really need to do is find the von Mises stress. If we're given the stress state, all I did was I found the von Mises stress using that formula. I know that is equal to 2p, and then we know that 2p is our von Mises stress is equal to the yield stress, which we found is 300. Therefore, p is also equal to 150. So in this particular case, they report the same thing, but also don't get used to that because there are cases where the Tresca and the von Mises will report different ones. So if you answered question 33 and you go to question 34 and say, oh, it must be the same, well, this was more or less just a fluke. Now, there are ways of knowing if it's a fluke or not, but I just want you to be aware of that. Trust the math. Don't try and do any tricky stuff on that question. All right. 35 says that the shown two-dimensional beam deforms such that the vertical lines stay vertical, vertical lines keep their original length, and the new horizontal position function is given by x1 is equal to big X1 plus u1, where u1 is a function of x1. It says that the center line of the beam deforms according to the function y, which is also a function of x1. It says then the following strain matrix of the function of the position function is given by, and all you need to do is actually create your position function. So we know in the horizontal direction it was given as this. In the vertical direction it's more or less given as this. And if we know the position function, we can find our displacement function. And if we know our displacement function, we can find our displacement gradient. Now remember, for displacement gradient, it's all about what everything is a function of because we're taking derivatives. That's why it's important to have as a function of x1 or a function of x2, etc. So if we were to go through and do our displacement gradients, we know that these last two terms are differentials with respect to x2. That's why they're equal to 0. Other than that, we just have our nice simple differentials. And then from there, we can apply it into our strain formula to get the following matrix, which is option D. So it's one of those ones where this actually isn't too bad of a question. I believe we actually went through it in class, so hopefully it's not too new or too much of a shocker to everybody. Again, all you have to do is make sure you know what everything is a function of, so when you get to the displacement gradients, there's no surprises. All right, question number 36. It says the following figure sketches the process of an orthogonal change of basis from the orthonormal basis set E1, E2 to the new orthogonal basis set E1 prime, E2 prime. If the components of U in the basis set B are 1, 1, then the components of U prime in the basis set B prime are equal to, and this is just a very standard change of basis question. We know that U prime is going to be equal to Q times U, so all we need is that coordinate transformation matrix. And if we look here, we know that the components of Q are going to be EI prime dotted with EJ. As we can see, it's not too bad at all. All you have to do is substitute everything in. And just like question 1 from above, if you look really closely, we can see that this is E1 prime, and we can see that this is E2 prime, or the rows. So there is a lot of simplification. After that, all you have to do is throw it into your calculator. You'll find it's 1.4 and 0.2, which is option A. Nice and simple. Question 37 is very similar, where it says the following figure sketches the process of rotating any vector by 30 degrees in the counterclockwise direction. The rotation matrix Q that can apply such rotation is, and this is where you have to remember the one trick we talked about when changing basis. If we're rotating a vector counterclockwise, this is the same as rotating a basis set clockwise. So all we actually need to do is find our Q matrix for a clockwise rotation of the basis set. You have them written down somewhere, I know you do. So all you need to do is find that Q, substitute the values in, and you'll find that this is equal to option number C. So it's actually pretty simple to do, not too bad. The key thing is if we're rotating a vector counterclockwise, we're actually rotating the basis clockwise. Not too bad. 38 gets a little bit more fun. It says given alpha, beta, and gamma, such that alpha, beta, gamma are greater than 0, a possible position function describing the shown two-dimensional configuration is given by. So basically on the left we have our original shape, I guess, and then on the right it's our shape after deformation. And all we need to do to find the position functions is just kind of see what happened to our shape. So I just made some pointers. We can see that all the points, oops, that's the eraser, definitely don't want that. All the points in our deformed configuration move up by that magnitude alpha. Remember from before, if I want to move something rigidly, I have to have plus a constant. So in this case, if I'm moving everything up in the x2 direction, I have to have that plus gamma in the x2 direction. So this eliminates option B, and this eliminates option C. Option C has the movement in the x1 direction, which we know is untrue. The second thing that we can see is we have expansion in the x1 direction, because before it was 1 and 1, but now it's 1 plus alpha, 1 plus alpha. We know that for expansion, all we need to do is just have that 1 plus alpha times x1, which is equal to x1 plus alpha times x1. So from there, we can actually figure out that it's equal to option A. It's also kind of a little trick to realize is that if we have an x1 and an x2 in the same row, this indicates some sort of shearing action is happening. If we look at our deformed shape, it still remains a nice square. So we know that there is actually going to be no shearing, which will also help gets you to the right answer. Moving on, we have question number 39, where the question says that the shown Euler-Bernoulli beam is subjected to a distributed load Q. If the beam has a Young's modulus E and Poisson's ratio nu, then the exact solution for all displacement y is given by, and basically it's just asking for the exact displacement. Now, Dr. Sammer was nice enough to give you the hint, but I would have given it to you anyway, and that is this. When it comes to these types of questions, you could solve for the exact displacement, but you're basically taking an integral 4 times and then applying boundary conditions. That's too much for a multiple choice question. If it was a written question, well, unfortunately you have to do it. But for this particular question, all you actually really need to do is just look at each one of the equations and make sure it satisfies the boundary conditions. So if we look at the very left-hand side of the beam, we have a pin, which basically means the displacement at that point has to be 0, and the second derivative at that point also has to be 0. Remember, second derivative is equivalent to moment. This basically means in our function that we can't have any constant terms and we can't have any x1 squared. If you remember from your assignments, and this was hopefully something that you picked up because I kind of asked for it as a comment, you will find that for simply supported beams, you couldn't have an x1 squared term. And the reason why is because then you would have a second derivative. Now, if we were to look at these functions, well, it's pretty easy to see. In the first one, A, we have an x1 squared term, therefore it's incorrect. Option B, x1 squared term, incorrect. Option C, we have an x1 squared term, incorrect. Therefore, we know it's automatically option D. So even though this question looks like it's going to be a lot of work, it's not too bad at all because we know it has to satisfy those boundary conditions. Question number 40. It's a big, long description. You don't really need to know it because all it's asking is for basically a function that satisfies essential boundary conditions. Essential boundary conditions. Now, the first thing that a lot of students are going to do is they're going to look up above and then they're going to say, okay, well, we know that the second derivative must be equal to 0, so we can't have an x1 squared term. But that's not true. Remember, essential boundary conditions are only related to displacement and rotation. So as we're going to see, our correct answer here does actually feature an x1 squared term when you factor it out, because again, it's not a part of the essential boundary conditions. Again, essential boundary conditions are just displacement and rotation. If we look at option A, we know that the displacement at the right-hand side of the beam, or when x1 is equal to L, well, that has to be 0. But if I substitute L, which is 1 in, this is equal to A3, which is not equal to 0. So we know that this is not a good candidate. Option B, if we were to expand it out to get the following, and we were to take the first derivative of at L, which is the rotation at L, we know that this is going to be equal to 2a3 plus 3a3, which does not equal 0, so we know that that's incorrect. And then finally, option D, y at 0, which is the displacement at 0, is equal to a3. Well, that's not equal to 0, so we know that this one's also not a suitable candidate. Again, it's not a hard question. The only trick you have to remember is that we are dealing with essential boundary conditions. If it was just the final displacement for the exact solution, well then C wouldn't work either. But C does work for the essential boundary conditions because we don't consider moment or shear as an essential boundary condition. It's just something to keep in mind. Question 41, kind of the same thing. It's asking for the potential energy of the system using the Rayleigh-Ritz method. Now this is actually pretty nice because for the Rayleigh-Ritz method, the potential energy is going to be the strain energy, which is this term right here, minus the work done on the system, which is this term right here. If we were to calculate work, it's just going to be negative Q times Y times dx1. And if we look here, we know what Q is, it's negative Q. We know what Y is over here, so if we take the integral, we get that the work done on the system is A2 L cubed Q divided by 6. So we know that all of the terms must have that in it. As we can see, only these two terms have it in it, A and B, or B and C. And this is, Q right here is just based on basically the work done on the system. So that's why you don't see a negative sign there. It's because Q was assumed going the opposite direction, but you guys know what's going on. For the internal strain energy, we can find it over here because if we know what we know what Y is, we can find the derivative of Y And then if we were to square it, we get 4a2 squared. So we know that our strain energy is going to be 2a2 squared EI times L, which is that first term right here. At the end of the day, we're good to go. Again, just a quick note, because I know that probably some of you are confused why the answer is a positive, but I would say it's a negative. It's because in this question, I didn't do it, but what you could do is you can actually eliminate that negative sign, which would end up having, let me just go to purple here. This is equal to negative a2, and then when I minus the work becomes positive, and that's what happens. So it depends on which direction you assume q, but it's pretty self-explanatory in regards to the final answer. I don't think many of you will have too much of a problem. 42, it says if the virtual displacement y star is equal to this, is applied to the shown Euler Bernoulli beam with a triangular load with a maximum value of -1, then the external virtual work is given by, well, again, another easy question, because the external virtual work is just going to be q times y star integrated over the length of the beam. We know that q, since it's linear, has the following relationship. So from there, all I have to do is just substitute everything into my equation, integrate from 0 to L, or the length of the beam. I get that this is equal to AL cubed divided by 12. So it's one of those things that this may be a little bit harder in an in-person exam, but you all have access to Mathematica. So you guys are going to be doing this in 2 seconds. Not even. It's that easy to do. So nothing to really worry about yet. It says, in a beam under axial load, situated with the longitudinal axis aligned with the coordinate axis x1, in general, the only non-zero stress component is, well, we know that this is actually going to be just sigma 1, 1. It's one of those things that if you want a better proof, you can go look at the theory. But for beams under this axial load, we only have one stress component, which is sigma 1, 1. We know that in actuality, there would be more, but they're assumed to be equal to 0 because we ignore those Poisson effects when we consider this situation. One of those questions that it's kind of a trick question, but I think most of you will get it. All you would have to do is go look at the theory. I explicitly say that there's only one component. You're all good to go. Question 44 says, if a linear elastic isotropic material is in a state of pure hydrostatic stress, then the following is true about the strain energy per unit volume. You guys are seeing my terrible reading skills come to life as I go through this exam. Now, if we have something that is in pure hydrostatic stress, remember we said that there's actually no shearing. And if that's the case, our von Mises stress is actually equal to 0 in this case. Now this is important because our deviatoric strain energy, which is our von Mises stress squared divided by 6g, well, that's going to be equal to 0. If our von Mises is 0, well then this has to be equal to 0. Now this is important because our total energy is equal to the deviatoric plus our volumetric, and if our deviatoric is equal to 0, then our total energy is simply volumetric energy, which is going to be option A. So not a bad question. I think most of you will get that, no problem. And if we look at 45, it's the same question, but now it's under a different stress state, and as we can see, this is under pure shear. Now under pure shear, our hydrostatic stress, which is the trace of sigma divided by 3, so if we look at the trace here, it's actually equal to 0. We know that our volumetric energy, which is p squared divided by 2k, that's going to be equal to 0. So in this case, our total energy is purely deviatoric energy. So it's kind of the opposite of what we just had in the question above. Not too bad though. I think, again, most of you will get these two questions. 46 says, a state of stress in a linear elastic isotropic material is such that the deviatoric energy is equal to the volumetric energy. Then the following is true about the relationship between von Mises stress and the hydrostatic stress. So the key here, of course, which we can get right from the question, is that the two energies must be equal. And since we know the two energy formulas, we can have this relationship right here. And basically all we want to do is solve for the von Mises stress. So we know that the von Mises stress squared is 3g divided by k times p squared. And all I have to do is substitute what g and k are. They're right from your formula sheets. And after simplification, you will find that this is 9 multiplied by 1 minus 2 nu divided by 2 multiplied by 1 plus nu times p squared, which is option A. So it's just a little bit of rearranging the algebra in this question. There's not really any tricks. Question 47, kind of a trick to this one, where it says that the longitudinal engineering strains on the surface of a test specimen were measured using a strain rosette to be 0.02, negative 0.01, and 0.01 along the three directions A, B, and C, where A is 1, 0, B is 1, 1, and C is negative 1, 1. If the material is assumed to be in small strain state, then what is the strain component epsilon 1. Now this is a tricky question because we know that epsilon 1 is the strain along the basis vector E1, which is 1, 0. Now this is nice because if we look at our directions that were measured, specifically direction A, we measured along this actual direction. So we know that the strain component is actually going to be the strain along A, which was found to be 0.02. So that's all you do for this question. Where it becomes difficult, which didn't really feature in this question, is when they ask you for a strain component that was along a direction that was not given. So that's where it gets a little bit difficult. Don't worry though, in the 2015 example, we will cover that case, or the 2015 final exam. It's not in this one though. Alright, kind of wrapping up the final here, it says consider the following cantilever beam with a distributed load Q. It says the beam is supported such that at the end where x1 is equal to L, the boundary conditions are y, which is equal to the derivative of y, is equal to 0. This right here basically means that it is fixed at this location. So what I did is I just drew kind of that fixed end to help us get a better understanding of what's going on in this beam. It says that the beam has a rectangular cross-sectional area. Now there's three questions associated with this one. And the first one is, what is the maximum von Mises stress? Second one is, what is the maximum positive sigma 1 stress? And then 50 is the maximum shear stress. Now what I like to do is I like to do 49 and 50 first, because we know that for a von Mises stress, which is question 48, it's basically the largest combination of sigma 1 and sigma 2. So if we can pinpoint where the largest sigma 1 and 2 are, we can have a good understanding of where the maximum von Mises is expected. So if we look at 49, we know that sigma 1 is equal to negative m times x2 divided by I. Now I is constant throughout the beam, so it's actually not going to play a role. So what we're going to look at is the top two terms. The first one is moment. So we know that the highest sigma 1 is going to occur where we have the highest moment. Now if we look at a cantilever beam, we know that the highest moment is going to happen at the support. So it's going to have to be either A, D, or C, which is actually pretty nice because if we actually look here, point F is not on it. We have A, D, or C. Point A is also not on it. So now we're actually limited to just B and C. So that's when we look at the second term, which is x2. Now, what it means is we want this term as high as possible. So what we need to do is we need to go further away from the x2 axis, or the x1 axis. We need to maximize that x2. So we know that if we're comparing points C and E, they're actually the same. But then we have to look at the last part of the question, which is the maximum positive. So if we were to look at this one, we know that positive means tension, and a cantilever beam under loading, this would occur at the top. Therefore, it's going to be point E. So again, the process is as follows. Look for the highest moment. Look for the distance away from the x1 axis. In this case, they were the same for D or E and C. And then from there, just figure out which side would be in tension. For 50, it's kind of the same procedure where we have our nice formula for shear, which is VQ divided by IB. So we want to look at V, which is our highest shear location. And then for Q, what you will find is that the shear is highest along the x1 axis. So the shear at the edges of the beam is actually equal to 0, and the shear at the midpoint is actually the highest. So what we want to do is find the location with the highest shear at the midpoint. Well, just like the bending moment, we know that the highest shear is going to occur along the support over here, and we want that midpoint value. And as we can see, that midpoint value is actually option D. So we can solve 49 and 50. The last one is the maximum von Mises stress occurs at, and then gives you point A, F, E, and then both A and B are correct. So all we want to do is look for the largest combination. So what I would do is I would circle in purple here the points. It's saying it's going to be point A, it's going to be point F, it's going to be point C, over here, and all I have to do is compare. Well, we already know that C has the highest location of sigma 1, 1, so we know that in this case it's actually going to be point E. If you're ever given a thing where it's asking you to compare, let me just erase it. Let's say this point right here where we were to compare point D and point C, well, it gets a little bit harder because remember, D is the location of maximum shear, but C is the location of maximum moment. Well, C and E together. So if that was the case, usually it's maximum moment that governs because moment is typically much higher than shear. It's almost always higher than shear, but some cases you can play around with it so it doesn't. You'll never see a question like this from me unless it's obvious. I would never make you try and fiddle around by figuring out which one is which. So hopefully that makes sense. All right, the last question. It says let x, y, and z be 3 by 1 vectors. Then all the quantities are three-dimensional vectors except, well, all we have to do is go through it. Now, if we were to look at A, we have the dot product up top, which is a scalar, divided by the norm, so we still have a scalar, but then we multiply it by a vector, which gives us a vector. So that's going to be a vector. If we look at option B, we have the norm of a vector squared, which would be a scalar, but then we multiply it by a vector, so that's also going to be a vector. If we look at option C, we have the cross product, which gives us a vector, but then we take the norm, which gives us a scalar. So we know that option C is going to be the one we want, but just for fun, we'll look at option D, where we have the cross product, which gives us a vector, so we know that that one's also good to go. So that's it for this final exam review. I know I went pretty quick in some spots because it's still a pretty beefy review, even though I'm just talking over and over and over again. So I hope I was able to help answer some of the questions you have. But remember, if you have any questions, just let me know because I'm always here to help. I want you to all feel nice and happy going into the final. And better yet, I want you to feel nice and happy coming out of the final. So thank you so much for listening. I really appreciate it. I will see you in the next final exam review.